Hello everybody, I am Dr. Gor Sarkisian and this is Chemistry 301 Biochemistry second course. And we will begin the course with chapter 13 in your book, which discusses bioenergetics and biochemical reaction types. A fundamental property of all living things is to perform work, to stay alive, to grow, and to reproduce. And to do so, living creatures need to be able to harness energy from their environment to channel this energy to perform biological work. It is a fundamental process of all living things, meaning all living things perform this kind of energy transfer, and it is quite ubiquitous in animal and plant kingdoms. So, what does it mean? We take chemical energy in a form of food or any other form of energy, and we are able to synthesize complex macromolecules which are highly organized from fairly simple precursors. We can establish concentration gradients of molecules across the membranes. We can generate electrochemical potentials, which then we can use as energy sources to perform a number of biochemical reactions. And we have talked about this, and you should know from previous courses, such as generation of electrons, carrying them with through NADH and FADH2 to be able to synthesize, for example, ATP, and to drive membrane cross-membrane transports using electrochemical gradients, for example. We can use this energy to perform motion, and in some creatures can generate light, such as fireflies, for example. Photosynthetic organisms, their fundamental source of energy is solar radiation, which they use to progress chemical reactions to form these biochemically necessary fuel molecules, again, such as sugar and downstream an ATP. When speaking about the beginnings of modern chemistry, we have to remember the name Lavoisier, who was a French nobleman and a chemist in the 18th century. He was the first to recognize the role of oxygen in combustion. He was the one to name oxygen and hydrogen. And in terms of biochemistry, he observed that respiration is basically nothing more than slow and controlled combustion of carbon and hydrogen. Today we know, and it's widely recognized, that biological energy transduction obeys the same laws as anything else in nature. It is therefore important to understand how they apply to the flow of energy in biological systems. So today we will review the laws of thermodynamics. It's going to be a brief review, and I hope that it's not going to be too boring for all of you. So we will also review the quantitative relationship between the free energy, enthalpy, and entropy. We will not go too deep into this. I will skip a few slides. The presentation is online, so you can make notes on that if you'd like. We will describe the specific role of ATP from the chemistry perspective in biological energy exchange system. And we will talk about oxidation reduction reactions, the energetics of electron transfer reactions. We know what electron transfer system is. Now we will discuss the energetics of it. And we will talk about how the cofactors in electron transport operate, and the enzymes and that catalyze these reactions, and how do they do that on a chemical level. So without further ado, let's dive into it. Bioenergetics and thermodynamics. So as we know very well, for any physical or chemical change, the total amount of energy in the universe remains constant. Energy may change form, or it may be transformed from one region to another, but it cannot be created or destroyed. Now that's the first law of thermodynamics. The second law of thermodynamics is all natural processes, the entropy of the universe increases. This is very important also to recognize, because when we're talking about biological systems, it seems to violate this law, because biological systems are quite orderly. Therefore, the entropy in biological systems is relatively low. So that's why it is a fact of life that the second law of thermodynamics governs some of the fundamental biochemistry. So I will skip through these 3 slides. This is just a general description what Gibbs free energy is, what enthalpy is, what entropy is. So here is a table of some of the fundamental constants that are very important when talking about, well, any chemistry. First one is Boltzmann constant, which basically relates to the average kinetic energy of a particle in a gas with as a function of its temperature. That is based on the observation that an increase in the temperature also increases the speed of individual molecules. And furthermore, all gases at given temperature will have the same internal kinetic energy. Avogadro's number is obviously the number of molecules in 1 mole of substance. Faraday's constant is the magnitude of electric charge per mole of electrons, and so on and so forth. So as we spoke about this in the previous course, cells are isothermal systems. That basically means that they operate at a constant temperature. Therefore, heat as such is not a source of energy for cells. What does that mean? Whenever we need a source of energy to perform work, we need to have flow of energy. If we have no heat gradients here, we cannot use that heat to perform work. There is no flow. Okay, just like in an example of waterfall, we can use that water to generate electricity through turbines, because there is a difference in the potential energy in a waterfall. Obviously, if there is no potential energy, if the levels before and after are the same, there is no longer flow, and we no longer can perform work. So in cells or in living systems, it is the utilization of the free energy that is the main source of energy. It is described by Gibbs free energy function, G. What does it give us? It can predict the direction of the reaction. G, the delta G, the change in G could be either positive or negative. It can yield the exact equilibrium position of the chemical reaction. And the amount of work that a given reaction can perform. Theoretically, because there is always some loss, but it denotes that it assumes that everything is occurs at constant temperature and pressure. And you should remember what that means from previous physics classes. So as we know, the standard free energy change is directly related to equilibrium constant. So the composition of reaction system tends to continue changing until equilibrium is reached, obviously. And by reaction system, we assume the product and reactants. At the equilibrium concentration of the reactant and products, the rate of forward and reverse reactions is exactly the same. There is no net change in a reaction system, and obviously there is no flow, and at these conditions, there is no free energy to be used to perform any other work. We have a model reaction presented here in which a certain concentration of substance A is being reacted with a certain concentration of substance B, and as a result of this reaction, we get a substance C and D. And I just realized that in the presentation I posted online, I have a little problem here. I had the concentration of CD divided by concentration of CD, equilibrium constant of 1. I hope not. Anyways, and here I still have a problem because this should be obviously A, and this should be B. Anyways, so equilibrium constant is the final concentration of the product divided by the final concentration of the reactants. So when we reach an equilibrium, I'm so sorry. When we reach an equilibrium, the delta G becomes, obviously, the change in free energy becomes 0. So when the system is not at equilibrium, it is driven towards equilibrium, and there is a driving force. The magnitude of this force is expressed in free energy for the reaction, or free energy change, rather, the delta G. And it is defined in under standard conditions, which is 25 degrees Celsius or 298 degrees Kelvin. When the product and the reactants are present in 1 molar concentration each. And for gases, it is with a partial pressure of 1 atmosphere. Therefore, the driving force towards equilibrium is our standard free energy change. So here is an interesting observation here that under such conditions, reactions that involve hydrogen, which are quite prevalent in biological systems, obviously the concentration of hydrogen under standard conditions would be 1 molar or pH of 0. But in biological systems, most biochemical reactions occur at nearly pH of 7. Biological systems are very well buffered. And the water concentration is highly concentrated at 55.5 molar, and it remains essentially constant. So for practical purposes, in any of the biochemical reactions, we assume that gain of loss of water is 0. So it is, I hope, quite obvious that describing biochemical processes at pH of 0 could potentially be a problem. Therefore, when we talk about biochemistry, we talk about pH being at, or hydrogen concentration being at 10 to the minus 7, or pH of 7, water concentration being constant 55.5 molar, and reactions that include magnesium ion. I have briefly touched about magnesium, and we will talk a bit more in detail, and the importance of magnesium in shuttling or the reactions involving ATP. Because we have changed these standard conditions, the physical constants for biochemical reactions, the standard conditions would be now called standard transformed conditions, and they are denoted with delta G prime 0 and K prime equilibrium. So what is the simple relationship between equilibrium constant and delta G prime 0, or K prime equilibrium, and the direction of chemical reaction? So we can have K prime equilibrium only as more than 1, 1, or less than 1. Now, if the equilibrium constant is more than 1, then our delta G is negative. If equilibrium constant is 1, then we have no potential delta G is 0. And if it's less than 1, obviously the delta G is positive. And corresponding negative proceeds forward, 0, nothing, positive proceeds in reverse. So here is a quick demonstration of what's happening. Let's consider an equilibrium reaction between glucose 1-phosphate and glucose 6-phosphate. And I hope you remember that this 1 denotes which carbon the phosphate is added to in a sugar molecule. So let's assume that we start with 20 millimolar of glucose 1-phosphate, and a final mixture is at 25 degrees Celsius and pH of 7. This tells us that this is under biological conditions. And at the end, we get 19 molar of glucose 1-phosphate and 1 millimolar, 19 millimolar glucose 1-phosphate and 1 millimolar glucose 6-phosphate. Obviously, here we have enzymes involved, but all they do is speed up reactions, and they do not affect the final concentrations of the reactant and product. So let's dive into it. And here the equilibrium constant obviously would be 19 over 1. And if you remember that delta G is minus RT natural log of K equilibrium. And if you remember, R equals to 8.315 joules per mole, and our T is at 25 degrees Celsius, but we have to present it in Kelvin because we're talking about energies here. 298 Kelvin. So delta G is therefore equals to 8.315 joules per mole Kelvin times 298 Kelvin times ln of 19, oops, sorry about that, ln of 19, which equals negative 7.3, sorry about that, this is kilojoules, that's right, kilojoules per mole. That's times K here. Okay, fairly simple. We don't deviate from our standard conditions too much. All we do is we assume pH 7 and we do our calculations at T equals 298 Kelvin. So here's a table of some of the common biochemical reactions and their associated delta G's, delta G prime zeros. Now, in a right column, we have the same values represented in kilojoules per mole or kilocalories per mole. Same number, different measuring units. So we will talk about some of these reactions in a bit more detail. One reaction, obviously, that you should remember, or two reactions here, or maybe even three, is the ATP hydrolysis to ADP plus inorganic phosphate, which is minus 30.5, and ATP hydrolysis to AMP, adenosine monophosphate, with release of PPI, which is double phosphates, which actually has a larger, obviously, free energy of minus 45.6. And the hydrolysis of phosphate into two inorganic phosphates, which is a minus 19.2. So it's basically these three reactions, and this one is, we will talk about this one. It has very interesting properties in the biological systems. So here's a brief refresher, the difference between free energy change, the delta G, and the standard free energy change, which is delta G prime 0. So for each chemical reaction, we have characteristic standard free energy change, which may be positive, negative, or zero, depending on the equilibrium constant. So the standard free energy change tells us in which direction and how far a reaction will proceed until equilibrium, when the initial concentration of each compound is 1 mole, pH of 7 and temperature of 25. If we're talking about gas, obviously 1 atmosphere, or 101.3 kilopascals. Therefore, delta G is a constant for a given reaction. Okay, this does not change. That's important to remember. The delta G prime 0, the standard free energy change, is indicative to the chemical reaction itself. Now the free energy change, the delta G. It's actually a function of product or reactant over the product, and that relationship is dynamic during the chemical reaction. Therefore, delta G changes during the chemical reaction, whereas delta G prime 0 it depends on an equilibrium constant, and this is a constant, okay? This does not change. Therefore, this number is a constant for a given chemical reaction. So if we have a delta G in a reaction that proceeds spontaneously toward its equilibrium, we have a delta G that is negative. So because this delta G is negative, it forces the chemical reaction towards its equilibrium. At the equilibrium, the delta G is 0, and there is no more reaction occurring. So let's write this down. We're assuming that this number has become 0, the delta G is 0. Therefore, if we rearrange this right here, and this is 0, therefore this portion is now actually our K equilibrium. We have reached equilibrium, right? And if we rearrange this, we obtain our initial standard free energy change equation, which is now indicative of this particular reaction. This is constant. When it comes to chemical reactions in biological systems, there are rarely cases in which there is only one reaction occurring. Reactions in biological systems are usually sequential. So let's assume we have A to B reaction, which is an equilibrium reaction, and then we have B to C, another equilibrium reaction. And of course, these are different reactions. Each of them has its own equilibrium constant, which please note is a function of product and the reactants. And if they both have different equilibrium constants, that means they both have different standard free energy changes. Because these are sequential, then we can assume that the overall reaction is actually A to C. Therefore, the standard free energy change for the whole reaction is the total of delta G prime 01 and delta G prime 02. So, and this is quite linear, and it's basically the sum of the two. So here's a very standard example. Glucose plus inorganic phosphate, which yields glucose 6-phosphate, plus H2O, which is a dehydration reaction. And I hope you remember this reaction is the first step in glycolysis. It's catalyzed by hexokinase. Now the delta G prime 0 for this reaction is 13.8 kilojoules per mole. Let this reaction, these two compounds sit with each other for 10 years, they're not going to react spontaneously, obviously. So what do we do? ATP to the rescue. Now we have ATP, which when hydrolyzed yields ADP plus phosphate. Now this is already a good sign. We have a phosphate here, we have a phosphate here, and we have water here, and we have water here. Okay, so this reaction, if you remember, has a delta G of negative 30.5 kilojoules per mole. Now let's examine this from the perspective of equilibrium. Now, glucose 6-phosphate, that's our product, and reactants are glucose plus inorganic phosphate. The equilibrium constant of this reaction is 3.9 times 10 to the minus 3 reverse moles. Equilibrium constant for ADP plus phosphate over ATP is 2.0 times 10 to the 5th. Now the overall equilibrium reaction 3, which is the sum of the two reactions, is glucose 6-phosphate times ADP times phosphate over glucose times phosphate times ATP. And let's see, this right here, in addition to this, and this right here, in addition to that. So this is, as you can see, it's basically multiplying the two together, and we get 7.8 times 10 to minus 10 to 2 molar. So when coupling these two reactions together, we effectively increased um, the the equilibrium constant by a factor of 2 times 10 to the fifth. Right? Amongst many things, one other thing that favors this reaction is that the concentration of products in the biological systems in the cell are extremely low. Therefore, it also aids in driving this reaction forward. Now, what does this do? This obviously releases a, a phosphate group, and with that, it takes care of the large negative repulsion in ATP, resulting in ADP. And remember, we generated a free hydrogen ion here, which is now right here shielding this negative charge. And we have generated the phosphate here. And this molecule is actually in resonance with this right here, a phosphate with 4 oxygens with each having a negative charge, but of course with a shielded hydrogen plus here, so with total of -3 charge. The ATP has a delta G of, if you remember, minus 30.5 kilojoules per mole. So it is a highly exergonic, but luckily in biological systems there are mechanisms that keep it stable, and it is being hydrolyzed only under certain conditions. But this number is for standard conditions. If you remember, we talked about the standard conditions. But in a biological system, the conditions are not standard, and the actual free energy of hydrolysis of ATP in living systems varies significantly. So why? One of the reasons is that the concentration of ADP, ATP, and phosphate are not identical. And the concentration of the product, well, all of these, the concentration of all of these is less than 1 molar, which is defined as a standard condition. And in addition, the actual molecule of ATP is magnesium ATP 2 minus. There is actually a magnesium sitting right here, interacting with these two oxygens, stabilizing it. So in reality, the delta G for ATP hydrolysis in biological systems is significantly larger than this. It can be up to -65 kilojoules per mole. And we'll talk about this in further detail. Now let's look at the hydrolysis of ATP. So the first step of hydrolysis of ATP is the cleavage of the terminal phosphoric acid anhydrate bond, which is this one right here. So let's write this down. We have oxygen, phosphate, oxygen, double bond oxygen, oxygen, we have, of course, negative. And a water molecule comes in. We will not consider the steric hindrances here at the moment, but let's just look at the mechanism. So we have two electrons here that can perform nucleophilic attacks here. So we can have this electron interacting with the phosphate and releasing this electron to this oxygen here. And this reaction results in HPO4 minus 2, which is a phosphate, double bond oxygen, 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 negative charges, and OH plus an H plus, okay, and a plus ADP, of course. To recap, hydrolysis of ATP is an exergonic reaction, but ATP is relatively stable under pH 7, but can be easily catalyzed. In biological systems, they're not standard conditions. The reactant products are not at 1 molar at the beginning. ATP is found as an adduct with magnesium ion, actually both ATP and ADP. Therefore, when we talk about delta G, we have to talk about magnesium ATP 2 minus. And furthermore, in biological systems, the actual energy yield of ATP synthesis can be up to 65 kilojoules per mole. And this is known as phosphorylation potential, and it's denoted as delta GP. And I just noticed that in the presentation that I uploaded, there was a typo there also. Here are what our ADP and ATP look like in our cells. These two negative charges are somewhat shielded with magnesium, therefore repulsive forces between these two are significantly less, and of course the negative charges here are also reduced, and the whole molecule is more stable. And obviously the ADP is even more stable. Now let's attempt to solve a problem or determine the delta GP for human erythrocytes. And the information that we need from here, obviously, is the concentration of ATP, concentration of ADP, and concentration of phosphate. And let's try this. Let me open up a blank page here and do these calculations. Now, let's solve this problem. Here our goal is to determine delta GP of this hydrolysis reaction. Delta GP, we know that it equals to delta G prime 0, which is our standard free energy change, plus RT, natural log of concentration of one of the products, concentration of the phosphate, second product, divided by our reactant ATP. Okay. So we know that delta G prime 0, our standard free energy change, equals 30.5 kilojoules. And then we have to add to it this component right here. And this component is for the let's say 2.48 kilojoules per mole. And if you know what this is, that's basically RT. 200 Kelvin. And this we multiply by natural log from the previous slide, we found out that ATP for erythrocyte is 0.25 times 10 to the minus 3 millimolars, right? Then we multiply that by 1.65, which was the phosphate, times 10 to the minus 3. And we divide that by 2.25 times 10 to the minus 3. So this right here adds up to the ln of 1.8 times 10 to the minus 4. And altogether, our delta GP equals to minus 0.5 kilojoules per mole plus 21 kilojoules per mole. Therefore, for human erythrocytes, the delta GP is actually minus 50, almost minus 50 kilojoules per mole. Besides ATP, there are other phosphorylated compounds and thioesters that have large free energy change. And let's look at a very interesting example here that has a very, very large delta G or free energy, standard free energy change of minus 61.9 kilojoules per mole. It's this compound right here, phosphoenol pyruvate, PEP, which has obviously a phosphate group here linked to the pyruvate through an ester bond, which is right there. When it's hydrolyzed, we generate a pyruvate, but we generate it in the enol form, which is unstable. This form can easily and very quickly, and it does, it tautomerizes or changes its isoform to a more stable ketone form. Okay, and these arrows here represent the rate of reaction from enol to ketone, which is quite large, and from ketone to enol, which is very, very small. So, what is happening here? Right when the hydrolysis occurs, and we have this is our reactant, right? We have certain concentration, and this is our product. It has a certain concentration, and our equilibrium constant is natural log of product over reactant, right? And we're trying to reach here, and we're doing this by obviously trying to increase the product and decrease the reactant, right? But as we undergo this reaction, the product that we form is immediately removed from the solution. Removal of the solution may not necessarily mean taking it away somehow, but it continues reacting into yet another product, which is not the immediate product of our PEP. This is why the concentration of the product remains low, therefore it drives the reaction forward, which results in very, very large delta G prime 0. Now let's look at another interesting biochemical reaction, which is the hydrolysis of 3,1-bisphosphoglycerate. Okay, it has a phosphate group attached to the oxygen on C1, and when we hydrolyze this group here, of course we release the inorganic phosphate by cleaving this anhydrate bond here between the oxygen and the phosphate. Now this reaction releases energy of minus 49.3 kilojoules per mole. Why such a large energy release? It can also be explained just like the reaction before. We create 3-phosphoglyceric acid, which is very rapidly ionized into phosphoglycerate. So effectively, it removes the product from the solution, and by creating this resonance stabilized secondary product, it reduces the immediate product concentration and drives this reaction forward. And here is another reaction that upon hydrolyzation of this phosphate that is attached to a nitrogen, the product undergoes such resonance stabilization, which again contributes to reduction in product concentration, the immediate product concentration, which drives the reaction forward and therefore increases the overall delta G prime 0. With this, we will conclude our lecture for today. We will pick up next time with thioesters, and hopefully next time would be an in-person lecture on campus. Thank you.